So think about this. You have these incredibly powerful language models, right? But their whole universe, everything they know, it's just text. Sequences of numbers, really. How on earth does something like that get a sense of, well, space or distance?
That's precisely the puzzle.
Yeah.
And what researchers are finding, especially looking at models like Claude 3.5 Haiku, is pretty fascinating. Take a really common task, breaking lines in fixed-width text, like in code or old-school terminals.
Right. The model has to know when to hit enter.
Exactly. And to do that, it needs to count characters on the current line, know the width limit, say 80 characters, and then check if the next word will fit. It sounds like simple arithmetic, but here's the twist. The model doesn't really do arithmetic for this. It builds a geometric map.
A geometric map. Okay, you've got my attention. We're diving deep today into how these LLMs, specifically Haiku, handle this seemingly simple counting. It's less about adding numbers and more about, well, geometry.
It really is. The model has to learn these specialized internal mechanisms, sort of like internal rulers, just to track its position relative to that line break.
Internal rulers built from text. Okay. Before we unpack how it builds those, just want to mention this deep dive is sponsored by embersilk.com. If you're looking into AI education or integration, check them out at embersilk.com. All right, so geometry. You said the model represents the character count, maybe from 1 to, say, 150 characters, not as a number line, but as a map. What does that map look like?
Yeah, so it's not just a straight line in one dimension. They call it a feature manifold. Imagine taking that simple count, 1, 2, 3, up to 150 plus, and instead of laying it flat, the model embeds it onto this continuous curved line. Think of it like a twisting helix shape, but existing in maybe a six-dimensional space.
Whoa, okay. A helix? In 6D, why make it so complex just to count characters on a line? Seems counterintuitive.
It does at first glance, but think about it. If you cram 150 points onto a tiny straight line segment inside the model's high-dimensional space, they get really crowded. It's hard to tell 41 from 42. By wrapping it into a helix, you use the extra dimensions to spread things out. Points that are neighbors in the count, like 41 and 42, stay close on the curve, but the overall curve stretches out. This structure, it's actually quite efficient. Researchers noted it's analogous to place cells we see in mammal brains for navigation. It maximizes the resolution, the ability to tell counts apart without using up too much internal capacity.
So it's like trading simplicity for clarity. The complex shape makes distinguishing nearby counts much easier for the model. Wild. Okay, so the model knows its current position on this helix count map. How does it compare that position to the line width limit? That's the crucial comparison, right?
Right, and that's where these specialized components, they call them boundary heads, come in. These are specific parts of the attention mechanism. And they learn a really neat trick. They essentially perform a geometric transformation. They learn to sort of twist that character count helix.
Twist it.
Yeah, twist it. So it aligns with another representation, the one for the line width, but it's a specific offset, like lining up two curved rulers.
Okay, so it's not just subtracting numbers, it's physically, well, virtually physically, manipulating these geometric shapes.
Precisely. It's a nonlinear twist. And the payoff is this. When the current count gets close to the boundary, within a certain range, this twisting action results in a really high alignment score, a big inner product in attention terms. That high score signals boundary approaching. And get this, it uses multiple boundary heads, each twisting at a slightly different offset.
Ah, like getting different perspectives.
Exactly. It creates this kind of stereoscopic view, allowing it to calculate the remaining characters with really high precision.
Okay, so this complex geometry for counting and comparing, does it make the final decision simpler? Deciding whether the next word actually fits.
That's the beautiful part, yes. After all that geometric work to figure out precisely how many characters are left, the final step is surprisingly elegant. The model represents the character's remaining value and the length of the next word in ways that are almost perpendicular to each other, geometrically speaking.
Right.
Orthogonal subspaces.
Perpendicular, like at right angles.
Pretty much. And because they're set up orthogonally, the decision is the word longer than the remaining space becomes incredibly simple. It's just a linear separation, like drawing a straight line or technically a hyperplane between fits and doesn't fit.
Wow. All that complexity boiling down to a simple geometric slice, that's quite something. So if these counting mechanisms are learned, geometric, almost perceptual things, can you mess with them? Like create an LLM optical illusion?
You absolutely can. And they did. There was this experiment where they inserted a string at just two add symbols, often used as a code delimiter, but totally out of context in the test prompt.
What happened?
It totally threw the model off. the attention heads, the boundary heads that were supposed to be tracking the character count from the last new line, they got distracted by the adlet at vir. They seemed to misapply a learned rule, thinking the add was some kind of reset signal or something important for counting, even though it wasn't.
So the counting mechanism got hijacked.
Exactly. The model suddenly started underestimating the character count, thinking it had way more space left than it did. It started breaking lines way too early. It shows that these aren't just abstract calculations. They're learned mechanisms, sensitive to context, almost like perception. You can give the model a sort of geometric migraine by feeding it unexpected context.
That's incredible. So wrapping this up, what we're seeing is that deep inside these language models, they're not just processing sequences, they're building these rich internal geometric worlds to handle tasks like counting.
Right, they turn sequential information into a kind of spatial landscape they can navigate and measure. It suggests their internal understanding, if you want to call it that, is far more structured and, well, spatial than we might assume just from the term language model.
A geometric view hiding within the text. Absolutely fascinating. Well, if you found this deep dive into the hidden geometry of AI thought as interesting as we did, please do subscribe to the show and maybe leave us a 5-star review. It genuinely helps us keep these conversations going. Thanks for tuning in.